right, what I need you guys to do is in your notes, label it section 3.4. And section 3.4 is on concavity using the second derivative test. So that probably means a lot to you right there. What are you going to be doing today? Finding second derivatives is what you're going to be doing, yeah. Some of them are very, very simple. Others of them are a little bit more complex, but nothing more complex than you guys have already done. So, what I'm going to do first of all is draw a graph, and let's say that your graph looks like this. I'm going to label this 0. I'm going to label this point 4. 1, 2, 3, and 4. So looking at that graph, where do you know that there are critical numbers? If I label this CNs, are you okay with that? Okay, so critical number CNs. Where do you know that the critical numbers are? 0 and 2. And 2. Yeah, 0 and 2. Now we know that they're at 0 and 2. We know we have an x value of 0 because that is, what do we call this point right here? A relative minimum. Very nice. And then we also know that up here we have another one because it is a, what do we call that point? A relative maximum. So the critical numbers happen at 0 and they happen at 2. Now, the reason that they're critical numbers or relative max, relative minimums is because that is where the graph changes what? Direction. Very good. Where the graph changes direction. And we always found this by using, what did we do to find those critical numbers? Okay, put what equal to 0? We found the critical numbers by, we had to find the first derivative. We're going to expand on that today. We're going to find the second derivatives. And the second derivatives is going to help us find these points called points of inflection. And points of inflection help us identify intervals of concavity. What does that mean? Concave. We have two options for things being concave. They can be concave. Okay, yes, I see what you're saying. You're thinking polygons. Something can be concave up, or it can be concave down. Sounds like a cavity I'm not talking about, where this is not dental school. No, I believe if you do go to dental school, you'll have to take a calculus class. So maybe there's a correlation. I would bet money on it that at some point during that intensive a program, you'd have to take something like calculus. But anyway, that's a whole other story. I'll draw you some examples in here in just a minute. Let's talk about points of inflection first of all. So points of inflection are the points in a graph where a graph changes concavity. And that just means when it changes from being concave up to concave down. Or vice versa. It could go from concave down to concave up. So let's just talk about what something looks like if it's concave up. Take a wild guess. Concave up or concave down. What do you think this is?
Concave up.
This is concave up. Now, when something is concave up and only concave up, doesn't switch from being concave up to concave down, doesn't have a point of inflection. A point of inflection is the point at which it switches. So in other words, if this was not a parabola, if it kept going and then switched to going down, then it would have a point of inflection. Let's just make a note here that there is no point of inflection, and from now on, what I am going to do is abbreviate point of inflection as PI. Okay, point of inflection, critical numbers, CN, points of inflection, PI. And it's probably a good thing for you guys to get in the habit of doing that too, otherwise labeling all this stuff gets to be a pain. So, alright, here we go. Take a wild guess. Concave up or concave down? Concave down.
What's your face?
Concave down. Again, there is no PI. There is no point of inflection because it does not switch from one direction to the other. All right, when you are ready, I'm going to start a new page. Are you ready?
See.
Yeah. Yep. All right, I'm going to draw you now a graph that has. I'm going to actually go back to the first example that we were looking at, where the graph kind of did this. And this was 4, and this was 0, and we said that this point right here was 2. What is this part of the graph? If you had to identify it as being something, you would call it what? Concave up. So this part is, and I'm going to get really lazy here, and I'm not even going to write concave up. I'm going to go concave with an up arrow. Same thing down here. This is going to be concave with a down arrow because it's concave down. So this point right about here, this is what we're going to concentrate on finding today. This point right here, take a wild guess what that point is called. Very good. That is our point of inflection, which I am going to label as being PI. And the PI can be found by what, you guys?
Second derivative.
Found by finding, probably not very good grammar there, found by finding the second derivative. Now, if the second derivative of x is equal to 0, you have a point of inflection. You also have a point of inflection if the second derivative doesn't exist. In other words, you have divide by 0, square root of a negative, all those issues that we've talked about over and over and over again. So if you end up with a situation where you can figure out that the second derivative is equal to 0, any of those x values are called points of inflection. Same thing happens if the second derivative is ever, does not exist. So in other words, we are doing exactly the same thing we did when we found critical numbers and when we found relative maximums and minimums. We're just doing it using the second derivative test rather than the first derivative test. This right here, let me just add a little bit. These are our PIs. So in other words, when our second derivative equals 0, whatever x value makes our second derivative 0, that x value is a point of inflection. And it can be, right, yep, it can't be anything but that. When it's 0 or if it does not exist.
And if it's something else, it doesn't have.
Right, yep, exactly. All right, now a couple other things I just want to write down here quickly. If the second derivative is greater than 0, if the second derivative is greater than 0, take a wild guess. Is it concave up or concave down?
Up.
It is concave up. And then when the second derivative of some x value is less than 0, it is concave down. So we're going to have to do those regions things again. And if you get a negative number, it's concave down. If you get a positive number, it's concave up. So I feel like most of this is pretty straightforward. It's not anything really new. We're just taking it one step further with the second derivative test rather than just the first derivative test. So let's move on to an example. I have 2 examples to give you. I may only give you 1 example today, though it probably makes sense to do 2 because I'm not going to be here tomorrow, so probably will give you 2. All right, can I move on to a new page? Example. If you are toward the bottom of a page right now, you probably want to start a new page. F of x is equal to x to the 4th power minus 4x cubed. The first thing that you need to do is decide whether or not this function is continuous. Is the function continuous?
Yes.
Yes, it is continuous. If it's not continuous, identify places where it's not continuous. You cannot have a point of inflection there. You cannot have a relative minimum there. You cannot have a relative maximum there. So identify those values first so that you can be anticipating them later on in the problem. So yes, it is continuous. I'm going to make a little note of that right now. It is a continuous graph. You know it's continuous because it's a polynomial. All polynomials are continuous. All right, next thing we're going to do is find the first derivative. Because to do these, to find the second derivative, you have to have a first derivative. So help me out here. First derivative, enjoy this because it's not so bad. What is the first derivative? 4x cubed minus 12x squared. All right. Now, my suggestion would be, as you are working through these, my suggestion would be to find the critical numbers as you go. Because they later on sometimes are helpful. In fact, oftentimes they are helpful to just pick up those critical numbers along the way. So let's do that right now. First of all, critical numbers show up whenever this thing has an issue. This is a polynomial. Are there issues with polynomials? There are not. It's a continuous graph. There's no breaks. There's no holes. There's no divide by zeros. There's no square roots of negatives. So this is an okay graph. But what we need to do is put it equal to 0 and solve for x. You guys should be dreaming about that stuff now because you have done it so much already. So put it equal to 0. What can you factor out?
4x squared.
4x squared, I think. Yeah, so let's take a 4x squared out. And if you factor a 4x squared out, what are you left with?
X
Minus
3. All right. So what are critical numbers?
0 and 3.
X equals a positive 3 and x equals 0. We have 2 critical numbers. We have a critical number at 3. We have a critical number at 0. I'm going to label these as being CNs. Might be helpful later. Okay? Second derivative. Now, where do you go to find the second derivative? Do you use this thing right here, the factored form?
No.
You use whatever form is the easiest to find the second derivative of. Where am I going to go? Right here, 4x cubed minus 12x squared. Super easy. All right, second derivative. Second derivative is going to be equal to 12x squared minus 24x. Do we have any D&Es? Do we have divide by zeros? Do we have square roots of negatives? Nothing. No problems. All right, so we're going to put it equal to 0. We're going to do exactly the same thing that we've already done, but what are these x values going to get me? Points of inflection. They're going to get me PIs instead of CNs. Very good. What can I factor out? 12x. That's going to leave me with x minus 2. All right, so what values of x will get you 0? 2 2, and x equals 0. Okay, so what do we call these? Oh, PIs. Very nice. All right, so we have our PIs, and our job now is to do exactly the same thing we did before when we were finding relative max and relative mins. But what we need to do is set up our regions based on our PIs rather than our CNs. So what is the smallest PI? 0. So my first region that I'm going to check is from negative infinity to 0. And then I'm going to check from 0 to 2. And then I'm going to check from 2 to positive infinity. All right, so give me some x values that I can check in each one of these intervals. What can I check from negative infinity to 0? Negative 1. Thank you for not saying negative 1/9. Joy. All right, what about from 0 to 2? 1. And then what about from 2 to infinity?
3.
That would be fun. What'd you say?
Do we put the second derivative?
Yeah, you guys, you know what? We are checking the PI regions, which came from the second derivative. So you need to take these values of x and plug them into the second derivative, okay? So go to y equals, type in 12x squared minus 24x, get a value. I don't care what it is. All I care about is it positive or is it negative? So when you plug in a -1, do you get a positive or a negative?
Positive.
You get a positive. All right, so I'm going to write positive. Does that mean concave up or concave down? Concave up. Positive means up. So I'm just going to pull out up here. Write concave up if you want to, but I don't need you to do that. Or you could write up. You don't have to keep writing concave. What happens when you plug a 1 in?
Negative.
You get negative, which means concave down. And what happens if you plug a 3 in?
Positive.
You get a positive. And if it's positive, that means, again, that it is concave up. Now, today, I'm going to ask you guys simple things like this. Find points of inflection and give me the increasing and or the concave up and the concave down intervals. That's all you have to do. Your work now would be done. So you would give me these two values, x equals 2, x equals 0 are your PIs. And then you would give me these things. You would list that from negative infinity to 0, it's concave up. And then from 0 to 2, you would tell me it's concave down. And then from 2 to infinity, you would tell me that it is concave up. Now, what if I asked you guys to take it a step further and give me the relative max and mins? What would you do? Say that again?
Plug it into f of x.
Yeah, what do you plug into f of x? Where would you find relative max and mins? Do you use these?
No.
What do you use to find relative max and mins? Yeah, you gotta go back up to the first derivative, the critical numbers, you gotta go back up to here. So you would use these things. But I want to make a point to tell you this. Everyone listening to me, listen. Huge piece of information. Everyone listening? If you have a critical number that is exactly the same as a point of inflection, do we have any matching critical numbers and points of inflection?
Yes.
Those will not give you a relative max or a relative min. Okay?
Oh.
So if they are matching, you don't need to worry about them. Yes?
So would you just use all the other values to find them?
Yes. Yep, you can rule them out right away. So there's only one value left to check. What value do you need to check?
3.
It's only 3 because these zeros are matching. Since these are let's make a note that because these are matching, I'm going to write this out. Because they are equal, it is not a relative max or min. Yes.
I thought the points of inflection had to be 0 or do not exist. Like
say that again. Relative max or mins had to be.
No, you said the points of inflection for the second derivative had to be 0 or d and
The second derivative is the x value that makes it 0. So that's why we put the second derivative equal to 0. We factored it and we found the x values that made it 0. Yeah, yeah. The x's that make it 0 are what we call the points of inflection. If the x values that make it less than 0, those are concave down intervals, and greater than 0 concave up. All right. So the only place we can have a relative max or a relative min is at x equals 3, correct? So what I need you guys to do is take that 3 and plug it. Where do I plug it in? The original function. All right. And we have to decide whether or not it is going to be a relative max or a relative min. And there's more than one way to figure that out. But what is one way for you guys to figure out whether it's a relative max or a relative min? You could look at the graph, yes, but that would be cheating.
Use the table.
Look at this. X equals 3. When x is equal to 3, the graph is concave up. And if it's concave up, we've got a situation like this. No, we don't. That is, sometimes I get all confused with concave up and concave down. We have a situation like this, concave up, right?
Yeah.
So what is 3? Is it going to be a relative max or a relative min? It's going to be a relative minimum because it falls in a concave up region. So this x equals 3 is going to be a minimum. Help me out, you guys. 3, comma, I don't know what it is. Negative 27. And I got that from plugging that 3 back into the original function. Okay, yes, Joey?
So then, when possible, when trying to pick numbers to see if the regions or what the areas and stuff,
Yeah.
would you want to pick one that's a critical number? If possible.
You don't, sure, because that made it really easy. You didn't have to think about where the 3 was, but all you really need to know, let's say that one of your critical numbers, let's say it was a 4. Well, 4, you just got to figure out 4 falls in which region? Does it fall between negative infinity and 0? Does it fall between 0 and 2, or does it fall between 2 and infinity? Falls between 2 and infinity, so you would just, you know what I mean? So, but I would say yes, when you can, then you don't need to think about that. You would just go right to the 3 and find your answer, yeah. Okay? Yes?
What if it was 2?
What if it was 2?
Or
Well, it can't be 2 because 2 is a point of inflection. So 2 is where the graph is switching. So it can't be a relative max or a relative min. Okay? Can you guys do me a favor? Go to y equals, type in the original function. Type in the original function, please. And in your original function, I just want you guys to see the graph. I don't have it sketched on my paper, but I believe that the graph looks something like it's doing something like it's coming in, and it kind of looks like it's going to go concave up, but it doesn't. It kind of just skims right through. Am I right?
Yeah.
Looks roughly like this. So this first region right over in here, that is called the concave up region. Even though it doesn't make a complete U-looking shape, it's still considered a concave up region. And then when it hits 0, it starts to go down. You see the downward? You see this little hill, I guess, like underneath the hill? That's your concave down. And then it heads up again and makes a real looking concave up situation. You have a point of inflection at 0. So right here is when it switched from being concave up to concave down. And then as you're working down, you're going to get to an x value of 2, which is about right here. And that's when it switches directions and it starts to become concave up again. Okay? And then we also know that we have a relative minimum at 3, negative 27, which is that point right there. This is not a relative minimum because it's not in the dip like a valley or a peak of a graph. Okay? So you know what's really helpful? Look at the graph first. Look at the graph. Look at what you're looking for. That's so helpful. But I will say this: if you guys get to the test or or homework copy or whatever, and you get to a situation where you are relying on your calculator and you're not showing me any calculus, you understand you will not get credit for that, right? Because
What if you
any of you can type these into your calculator and get answers, but I need you guys to show me the calculus behind it.
What if you get it right?
What'd you say? Or China?
Oh, on the exam though, it's multiple choice, so
The exam is multiple choice. You are correct.
Yes.
we don't have to do work.
I will not. Yes, I know you will all do work, but I will not know if you do or do not. Now, China, you are making it sound like the exam is going to be so easy. We all know that.
No,
Will
I'm not
be-
saying it's
okay,
not.
okay.
I'm just saying on questions like this, you
Yeah,
can use
yes, absolutely. If I say what is the relative minimum of this graph, I would never know that you cheated.
Here's some fun.
She's so slick.
Yes.
I have a question about that.
Yeah.
Like last year on our exams, Zarnaki would have like, it would be multiple choice, and he said like if you do show work and you do get it wrong, you get like some points back.
Well,
So,
even on the final and midterm, you would do that too?
She
For
yeah.
everything.
Really?
She doesn't want to touch that.
I gotta think about that. My intention really is because I'm gonna have exams for all of my classes.
That's a lot of work.
It's a lot, and it's not that I'm okay with the a lot of work part of it, it's just that will I have time to get it all done? So, let me think through it a little bit more. I may be able to have a section where I will not check anything, maybe there'll be a portion where I will check a little bit, yeah.
What day do the grades have to be in by?
Our grades are due on Friday. Yeah, so you guys are all, you're gonna finish your, and I have classes all day on Thursday. My prep hour is on Wednesday, so I'm gonna have exams to grade, a lot of exams to grade.
You're talking about like 2 weeks Friday, right?
What'd you say?
You're talking about, like, okay.
They're not Scantron?
We gotta scan try, yeah.
Oh.
But then I gotta get them all in. There's so much that goes into just entering a grade into the computer.
How many Scantron machines do they have?
Well, this is all on video right now, which is making the video extra long. I'm sure my 2 calc kids in first hour are gonna appreciate this. We have 1 Scantron machine, but we have this new fancy copy machine. It's never really been an issue, except that the ink is starting to wear out on it, and they're not gonna replace the ink. So, but we do the copy machine right now has the ability to grade Scantrons. So, and we have been encouraged to do that method, but just a lot of us are real foggy on how to do it. So it's just a matter of us finding time to get instructed on how to do it.
So you guys have to share the
I was
machine?
just,
It all works out. We're all adults. We are very good sharers.
Except Mr. Coon.
Except Mr. Coon? Yeah, you're right.
He'll be watching this video. I'm
I
gonna tell him to
asked him
watch
something
this
and he's
video.
like, no, I don't help you. I was like, what the
What
heck?
did you ask him?
I asked if I could use a copy when he was done, he's like, no.
Oh, I thought you were going to say, well, how do you find the second derivative so I can find intervals of concavity? And I was like, well, no wonder he said no, because he doesn't know how to do that.
But I already knew how to do that.
he doesn't remember how to do that.
He doesn't remember. That's what I meant to say. Which means he doesn't know how to.
What
right
does
now.
he remember?
In Management, yeah. They don't know how to.
All right, let's go on. Oh, I already got it. All right, let's go on. We should do one more. Let's go. Ready, go, ready, go, ready, go.
Yeah, we have to.
I think great.
One more example. That's why I didn't stop the video. Example, f of x is equal to x squared plus 1 over x squared minus 4.
Don't tell me you gotta use the one thing.
The quotient rule? Yes.
Is this ever gonna go away?
No. Actually, I think, no. Maybe next unit we won't have to do that. All right. F of x equals x squared plus 1 over x squared minus 4. The first thing I said in that last problem was look for periods at which the graph does not exist. Are there any
Yes.
values of x at which the graph does not exist? Where is it?
X equals 2.
Positive and negative 2. So I'm going to make a little note here that the graph is not continuous at x equals positive and negative 2. And the reason that I need to know that is because I can't have a point of inflection there, and I cannot have a critical number there either. I can't have a relative max or I can have a critical number. I cannot have a relative max or a relative min there. So, all right, find the derivative. And I am definitely going to run out of room here, so I'm going to be swapping between pages. So I'm going to need some help from you guys. first derivative. Larissa, you sound just very excited about doing this. What do you do first?
X squared minus 4 times 2x minus
Good.
x squared plus 1 times 2x
Very nice.
over x squared minus 4 squared.
Very nice. Quotient rule to find the derivative. You got to clean this up, and we are going to clean this up by distributing this into this, this into this, which is going to get me 2x cubed minus 8x. All right. Now, this negative and the 2x have to be distributed into here. So I'm going to distribute them at the same time, which is going to get me negative 2x cubed minus 2x. Are you okay with that?
Yeah.
All right. All divided by x squared minus 4 quantity squared. The 2x cubes very conveniently cancel each other out, which is nice. So when I clean this up, I have negative 10x, right? All over x squared minus 4 quantity squared. Alright, so what we need to do now is find our critical numbers. Are there any values of x that would make the denominator equal to 0?
No.
Still positive and negative 2. Same situation that's going on here. So we have some critical numbers here at x is equal to positive and negative 2. Why do we know that those are not going to be a relative max or relative min?
She told us earlier.
Yeah, because, I said earlier, yes, but why did I say earlier that they couldn't be a relative max or a relative min? Yeah, it's not continuous. The graph does not exist at that point. It cannot be a relative max. It cannot be a relative min there. But we have to consider something else. We found the value of x that made the denominator equal to 0, but you also have to set the entire function, the entire derivative, equal to 0. Do you remember doing that?
Yeah.
So we have negative 10x over x squared minus 4 quantity squared. Put it equal to 0. Remember, this was like not even here.
Oh yeah.
Remember that? Ignore the denominator. Negative 10 times x equals 0 means that x equals what? 0. So we have critical numbers at positive and negative 2. We also have a critical number at 0.
Why did you cancel out x squared minus 4?
Well, what happens here is we have to solve for x, we got to get rid of the denominator. So we multiply the left side by the denominator, which cancels them out, and then we multiply the right side by it. And multiplying by 0 gets us nothing. So, all right. So we have an x value of 0. All right.
And that's a critical number, right?
And that is a critical number also. So we had to consider all options. What values make the bottom 0? And we also had to consider anything that made the overall derivative equal to 0.
Oh, this one's only gonna have a max or a min.
Yes. Yep. It's only going to have one max or one min, maybe, depending on what happens with the rest of the problem. But yes, it's looking like that. All right, now this is our first derivative. I'm going to flip pages here. I need you guys to tell me that again. The first derivative is equal to negative 10x over x squared minus 4 squared. We need to find the second derivative.
Yay.
Yay! Isn't that yay?
Said no one.
Right. Second derivative says that we take the denominator, which is x squared minus 4 squared. We're doing the quotient rule. Times the derivative of the numerator. What's the derivative of the numerator? Negative 10 minus the numerator, which is negative 10x, times the derivative of the denominator, and that's not going to be fun. How do I find the derivative of the denominator? The chain rule.
Multiply that.
Can I just say this? The chain rule, which you guys seem to really not like very much.
Nope.
I think I remember not liking it either when I was taking it. That was so many years ago, I can't quite remember. Let me just show you real quickly what you have been doing, and maybe if I show it to you real quickly in these simple words, it will make a little bit more sense to you. This is what you're doing when you do the chain rule. You take this power, and you throw it in front. Okay, so 2. And you throw it in front of this whole thing. So it's 2 times x squared minus 4. You subtract 1 from the power, which makes it a power of 1. And then you multiply, so I'm going to put the power of 1 there. And then you multiply it by the derivative of that thing that is squared. What's the derivative of the thing that is squared? 2x. There, done. That's what you've been doing. I think some of you are making the chain rule harder than it has to be.
You're missing a parenthesis.
Yes. Am I missing a parenthesis? Yep, you're right, I am. Okay. All right. And then the bottom is going to be x squared minus 4 to the power of 4. All right, let's clean this up. Now, just take my word for it right now. I want you to not do anything with this right now. I want you to keep it as x squared minus 4 quantity squared multiplied by negative 10. But let's clean up the rest. Again, leaving the x squared minus 4 as is. And you guys shouldn't, do you understand why I'm having you do that?
You'll show
We
us.
have an x squared minus 4 here, and we have another x squared minus 4 here. I am going to factor it out in just a minute. But let's clean up everything else around it. So we have a minus sign. What is negative 10x times 2 times 2x? Negative 10x times 2 is negative 20x
40x squared.
times negative 40x squared. Negative 40x squared. What do these two negatives get me though?
Positive.
Positive. So I'm going to make it longer, make it a positive instead. Plus 40x squared. Multiplied by x squared minus 4. Divided by x squared minus 4 to the power of 4. Alright, so they both have in it an x squared minus 4. The two top situations both have an x squared minus 4. I'm going to take that out. I'm going to factor it out. So when I factor it out, I'm going to be left with x squared minus 4. How many of them can I factor out?
3.
Well, we have 2 of them here, and I have 1 of them here. So I can only ever factor out the smallest number of them, which is x squared minus 4. And I'm gonna put a bracket here now, only so that I can kind of separate the thing that I factored out from the leftovers. So I factor out an x squared minus 4. What is left inside? A negative 10 and an x squared minus 4. Do you understand where the x squared minus 4 came from? I only factored 1 of them out, so I still have 1 left over. Plus 40x squared. Divided by x squared minus 4 to the power of 4. What can I do now? Yeah, this x squared minus 4, I can cancel out with what on the bottom? 1 of them. How many are going to be left? 3. So I'm going to cheat here, and I'm going to cross off my 4, and I'm going to make it a 3. Clean it up. I keep going here because I'm running out of room. Negative 10 times x squared, negative 10 times negative 4. Negative 10 times x squared is negative 10x squared. Negative 10 times negative 4 is positive 40 plus 40x squared. All divided by x squared minus 4 to the power of 3. Now I can combine the negative 10x squared and the 40x squared, which gets me 30x squared plus 40 all over x squared minus 4 cubed. I'm sorry, I have to apologize right now. I didn't do anything wrong. The same, it was not a very nice problem. But now what we need to do, all what we've done so far is found the second derivative. Now we need to find PIs, points of inflection. So, what value of x right here, you guys,
0.
would make the bottom of this thing 0? 2 x is equal to positive and negative 2. Those would get me 0. But they're also critical numbers. But they're also values of x which make it not continuous. Okay? So, but let's remember how we also have to put the top of this thing equal to 0? So I'm going to come over here to the side. 30x squared plus 40 equal to 0. Now, stop and think about what's going to happen right now. You are going to subtract 40. You get a negative, right? Then you are going to divide by 30, which is still going to get you a negative. And then you are going to have to take the square root of the negative. The square root of a negative. Imaginary numbers, we're not going to deal with imaginary numbers in this. I'm not going to throw that at you too. So when you get to a situation like this, where you're going to be taking the square root of a negative, it's not going to get you a critical number. There's no extra critical number here, so you can cross this part right off. So we have, not critical numbers, I meant to say points of inflection. No PIs there.
So you have none at all?
Sorry.
What did you say?
So you have none?
So I have none. Yep, because, yeah. Actually, hold on, no, let me back up. These are still PIs.
But you can't use them, right?
Well, we still have to check what's happening in those intervals. They are still PIs, and we just know we're not going to have a relative minimum there. We're not going to have a relative maximum there. They will still get me points at which it changes from concave up to concave down.
So we have to write, for critical numbers, we have to write -2 and 2.
Yes. Well, and
yeah.
PIs. Let me label those right now. I never did that.
There, I have a question.
Yeah.
Relative maximum because they're the same as equals numbers.
Yes. And because right off the bat, we said the graph did not exist at 2 and -2, so you know you cannot have a relative max or a minimum there. Okay? In a minute, we're going to go back. Actually, you might want to right now. Go back, go to y equals. Type in the original function. Take a look at your graph. You're going to see what's happening. You're going to have values at 2 and -2, x values at 2 and -2, and you're going to see how the graph jumps from being concave up to concave down. We have critical numbers, which is PIs. We have PIs at positive and -2. So the regions that we have to check are from -infinity to -2. We have to check from -2 to +2, and we have to check from 2 to positive infinity. So I need some values, some x values. What happens, or what x value falls from -infinity to -2? -3. What about from -2 to 2? Give me an x value that falls in that region.
0.
0. And then what falls in between 2 and infinity? Should be 3. So we have -3, 0, and 3. Where are you going to plug those into? Yeah, they're PIs, points of inflection, so you are going to plug them into your second derivative. And all I'm looking for is it positive or negative. And I got for -3, I got a positive. Do you guys agree with that?
Yep.
If it's positive, it means it's concave up. And then for 0, I got a negative.
Yep.
Agreed?
Yep.
Which means it's concave down. And then for 3, I got a positive again, which makes it concave up.
To find these regions, you use the PI.
Say that again?
To find these regions, you use the PI.
Yes, use the PIs, yep. Now, today, this might be all I asked for. I mean, I know it's a ton, but I mean, I wouldn't ask you to then go back and tell me the relative mins or maxes. I might just ask you for the PIs and then the regions of concavity. But I would like to talk about the relative max and mins. Yes.
I thought you said if it's a critical number in PI or whatever, then it isn't a maximum.
Very good. That's what I was going to say. No, seriously, that's right. That's exactly right. Our PIs match our critical numbers. So we know that though that positive and negative 2 is not going to be a relative max or min. But didn't we have another critical number?
0.
We had another critical number at 0. So I'm just going to list here that we had another critical number at 0. So what does that mean? Where does 0 fall, you guys? Where does 0 fall?
Negative.
Yeah, in a negative region. If it's negative, it's concave down. Well, if it's concave down, it looks like this, which means that 0 is going to be a maximum value. So that x equals 0 means that we have a relative max, and it's going to be at 0, comma, something. Where do I find that something?
Plug it into the original one.
To the original function. Very good. And I did not do that.
-1.